Okay. Yes, thank you. Thank you very much. Thank you all for being here, and thank you to, thank the organizer for giving me the chance of giving this presentation in this nice workshop today. I'm gonna talk about this couple of papers done with these wonderful collaborators. Many of them have been here in the past weeks, so you basically know many of them. And this talk is about this integrated correlator story that we have been hearing about in the last few weeks. Here there are no longer so many experts about this, so I will try to be as much pedagogical as I can, but please ask me questions and interrupt me whenever you want, also to keep it more entertaining. Let me start by giving some motivations. We have been hearing a lot about this integrated correlator story, which are in general, schematically. We can consider this class of 4-point function. Let's consider the simplest one, the 4-point function of 4 operators in n equal 4 super Yang-Mills theory in 4D, integrated with a certain special measure. And this in the dual picture corresponds to some 4-point scattering amplitudes. I will try to draw it in the best way possible, which somehow probe the ADS5 geometry. So this object corresponds to closed strings scattering. And in particular, we have seen that once that we integrate over the positions of these 4 operators, in the dual picture, we see that we can extract the coefficients of the various string corrections of these closed string scattering amplitudes, in particular for this case, scattering amplitudes of 4 gravitons. And in particular, if we define this object as a certain function, C, which depends on the modular parameter tau, tau bar, and n, this admits an expansion in the large coupling limit of this kind, and 2 minus 2g, some coefficient depending on the genus G of tau and tau bar. So it admits this closed string genus expansion, where in general these coefficients here can be expressed in terms of modular invariant function. Invariant. So this is more or less the picture for this class of integrated correlators. And the idea now is, the question that I'm asking in this seminar is, how can we generalize this picture to the case where we don't have only closed strings, but even open strings? We have seen in the previous week that a possible way is to reduce the amount of supersymmetry and consider special brane setups, including also D7 and in a very peculiar way in Chichester stock. But in my case, I will consider a special case where I consider the scattering amplitudes in presence of an extended brane here. So something like this. How can we achieve this kind of picture? This is in, let's say, ADS. From the dual CFT perspective, we will consider, in these 2 papers, I basically consider 2 possible examples of this class of scattering amplitudes. The first of all, the one that I will discuss the most, is contained in this paper, together with Gus Brown and Song-Kao Wen, where we consider the integrated correlator of this kind, this HH, LL, heavy, light correlators, with these particular features that the dimension of the operator that here I called h is equal to n. So this is a heavy operator in the planar limit, and as heavy, it kind of creates this classical prop particle in ADS without deforming the ADS5 geometry. The other example that I will briefly mention in the end is contained in the second paper, and it was also discussed by Pufu, Rodriguez, and Wang in a previous paper, is a similar class of integrated correlator, which instead here in the CFT side can be written in this way. A 3-point function of 2 operators or 2 in presence, let's say in general, of an extended line defect. And the picture in the dual sense will be something like this. We are inserting an extended object, a line object, in the CFT side. We have 2 additional insertions point. This is the equivalent in presence of a defect of this 4-point function. When going to ADS, we are creating a special worksheet in presence of a boundary, and we are basically computing this class of integrated correlator. Okay, so in this talk, I will mainly consider this class of integrated correlators. Okay, yes. That's a good point. I will be more precise in a moment. In particular, here, what we are discussing is the so-called giant graviton D3 brane. And as such, we will see that this picture is still modular invariant, and we can still have a similar topological expansion in terms of some modular invariant functions. Instead, in this case here, this is a line defect, which is dual to some extended string in ADS. And so this corresponds to scattering of, in general, PQ strings, where, I mean, P is the electric charge, Q is the magnetic charge, and, I mean, the most common example is to consider a Wilson line here, which corresponds to a 1-0 string here, so a fundamental string. If we consider the dual particle, which is the Toft line, corresponds to a 0-1 string. I will be more precise about both of these cases in the following. Are there other questions about this motivational part? In the following, I will, as I said, mainly consider this class of observables. I will, first of all, discuss properly the setup, which kind of operator we are inserting here as heavy, which kind of operator we are inserting here as light, and how we can actually compute then this integrated correlator in terms of this matrix model. To get then this kind of exact result in terms of an integrated correlator C. Okay, so let's move to the second part, the setup. For the heavy, heavy, light, light integrated correlator, as I said, we are considering as a light operator the simplest one, which is the one also discussed in previous cases, which can be written as trace of phi squared inserted in a position x, where in general this phi as a notation is a combination of the 6 scalar fields of n equal 4 super Yang-Mills. So I goes from 1 to 6. And this is a perfectly well-defined gauge invariant operator. His conformal dimension is fixed to be 2 because it's 1/2 BPS. This is also contained in the stress tensor multiplet. So in the dual picture corresponds to a scalar field which is in the same multiplet of the graviton multiplet. On the other hand, we consider a very special heavy operator, which is defined as d of x, which is written in this way, 1 over n factorial epsilon I1 epsilon n epsilon j1 epsilon jn phi. Here I'm writing explicitly the fundamental gauge indices I1 j1 phi in jn, where I k and jk goes from 1 to the n. So this is called in the field theory community a determinant operator, which is indeed a gauge invariant combination completely anti-symmetrized of these n scalar fields. And this is very interesting from many, from many point of view. So let's discuss some properties of this determinant operator. So first of all, yes, epsilon is the, yes, sorry. Yes, it's 2 epsilon, sorry, with n indices, sorry. Okay, so this is way more clear. Okay, so these are, as I said, fundamental indices. So this is a gauge invariant operator. And this can be considered as the n equal 4. Here we are, sorry, I forgot to mention at the beginning, but we are again in n equal 4 super Yang-Mills. The n equal 4 super Yang-Mills version of baryon-like fields, baryon-like operators. So somehow these are interesting also from this particle physics perspective, but also, yes. That's a very good point. Yes, in principle, yes. They can be rephrased in terms of somehow trace of phi to the n plus all the other multitraces. But here there will be n kind of these coefficients. And so somehow, even in the large n limit, this is not exactly like trace to phi to the n. So it is not exactly related to Kaluza-Klein modes. And this is very important for what I will discuss in the following. Yes, exactly. That's exactly the point. But yeah, there have been approaches from the purely perturbative point of view where people, kind of consider these objects trying to somehow swap, the two roles between determinant operators and maximal trace operators. But these are not exactly the case. Because, as I said, this is not true, okay? Because, sorry? Yeah, exactly. They scale like n, and there are n of them. So it's really a mixture of, n operators here, even more actually. They scale like, the partition of n somehow. So if n is very large, the number of operators here scales like factorially, I think, exponentially at least, with n. And also the coefficients grow very, very much in this large n limit. So yeah, thanks. This is a very important point. So this is exactly like this. So these are indeed very important from the field theory point of view, but also from the holography point of view. These are heavy operators, but not that heavy. Because, they are made of n scalar fields, so their conformal dimension of this D is exactly equal to n, and it does not renormalize thanks to the action of supersymmetry. These are still one half BPS. And this means that, they are heavy, but not enough to deform the geometry. So they cannot create a black hole or somehow something that deforms the ADS5 geometry. So they can be considered exactly as classical particles in ADS. Exactly, exactly. If they had, in principle, you can create, but only out of these traces. You can even create states. For example, there have been approaches, papers like where this h is considered to be trace of phi squared to the p, with p going like n squared. This is possible in this kind of setup. In this case, you are somehow creating a sort of black hole-like in the dual picture. But here we are explicitly considering not trace operator, but this kind of determinants. Yes, 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 absolutely, exactly. Okay, so yeah, they have this very interesting holographic behavior, and indeed, if we now start thinking about correlation functions of these operators, these are 1/2 BPS, as we said. So they have been studied in early ADS-CFT, so around 2000 to 2005. In particular, their 2-point and 3-point function are fixed by supersymmetry. And they are fixed to their free theory value. So they do not get any quantum corrections. And so, the interesting part starts at the level of 4-point function. The interesting from the quantum correction somehow starts at the level of 4-point function. And we consider somehow the simplest 4-point function, which is d inserted in x1, d x2, O2, x3, O2, x4. And this is, this can be fixed using superconformal symmetry to have a function which only depends on free theory parameters. So these are symmetry vectors and the insertion points, plus some prefactor which again depends on all the R-symmetry dependence, times a function hd that we call hd, which depends on u, v, tau, tau bar, and n, where u and v are the usual conformal cross ratios. So x1, 2 squared, x3, 4 squared, x1, 3 squared, x2, 4 squared, and v similarly. This is it. So somehow here the superconformal symmetry fixes this 4-point function, and the most important part somehow is this dynamical function, hd, and we will mostly concentrate on this function. Now, since, these are very peculiar objects, even at the field theory level, this function has been studied even at 1 loop and 2 loops order. This is not easy to compute. Indeed, there were approaches about, on this 4-point function only in 2019, using integrability techniques by Jiang, Komatsu, and Vescovi, and a very recent attempt at 3 loops, but no more than that. In particular, no non-perturbative approach for this class of correlation function in presence of these determinant operators. So somehow it's been very interesting to apply the formalism of this integrated correlator to this class of observables. And this is what we are going to discuss now. Are there any questions about the setup that we are using here? Yeah, you mean from the field theory point of view, how you can, from holography? Yeah, there are papers in this early ADS-CFT that, somehow show that their behavior actually is easily relatable to, the one of a D3 brane. Somehow we will see in this approach how this D3 brane behavior works out from this integrated correlator story using, the usual localization approach. But, from this explicit expression is not easy. What I can tell you now is that no one really started from a let's say, a D3 brane definition in flat space, and then trying to move to the curved space to realize these kind of setups in a standard approach somehow. Especially due to the fact that these are objects that scale like n, and so it's not easy because, I mean, they somehow influence the way you construct usually clustering states. I mean, this is something from that perspective quite new. Sorry. Yes, absolutely. In the field theory result, there are no non-perturbative approach for this 4-point function. This is what I'm saying. So the only approach to this 4-point function is one loop and two loop at small g mills. But there are no approaches for this 4-point function from the dual perspective. Absolutely. So let's now apply this integrated correlator story, and I will briefly review how it works. Just to give a hint of how these objects can be constructed in practice. I mean, one should start from, as we said, n equal 4 super m mills on the flat space. And for conveniency, we move using a conformal map to the force sphere of the same theory on the force sphere. And then we deform it. We use some deformations. We apply some deformation, preserving at least n equal to 2 supersymmetry. This is the prescription somehow. And in particular, starting from the n equal 4 action, we deform the action in the following way. We include some deformation parameters lambda a, which I call here like lambda a, which are associated to some integrated insertions on the sphere. Okay? The important point is that this deformation parameter that can be, there have been many examples. In particular, we will consider the massive deformation M, which breaks n equal 4 to n equal to 2, but also the squashing deformation B, which basically construct a sort of ellipsoid out of the force sphere. And in principle, there are even other of them. Once that we are at this point, we perform this localization, which is this very complicated procedure done by Pestun in 2007. And very schematically, the idea is that it allows to somehow solve the path integral of the theory. So we know that this is a very complicated, ill-defined object. It can be reduced using this localization that at least requires n equal to 2 supersymmetry down to a finite dimensional integral, d of a, and in this case, we remain with an integral over a Hermitian matrix, which is an n times n matrix, so it becomes a matrix model properly. And from this localization approach, we end up with this partition function in an n equal to 2 theory, which then will depend on the deformation parameter lambda alpha. And in particular, in our setup, we will consider only the massive deformation, M, plus some additional deformations, which we call tau d and tau bar somehow d, which are associated to the insertion of these determinant operators. And thanks to this massive deformation, we end up to this so-called n equal 2 star theory, which is the massive deformation of n equal 4. So this is more or less the picture. And now the idea is that if we take some derivative with respect to the source, lambda, this corresponds to some integrated insertions of these operators, okay? And so somehow now we perform this derivative and we go back to the flat space and we end up with some object which will have some integration measure that actually depends on the SUSY deformation that we perform here, to the conformal parameters in moving from the flat space to the sphere, depending on the 4 insertion points, and then these correlators of D, O2, O2. Because this is then equal to the derivative with respect to tau D and tau bar D, the double derivative with respect to the mass of the log of this partition function. Where then we put all the variables, tau D bar, and M equal to 0, restoring the original conformal symmetry and the original n equal to 4 symmetry. And this must be normalized by d tau D, d tau bar, d log of z, n equal to star. And so somehow we see that on one hand, we have something which is defined in n equal 4 and on the flat space, integrated over this special integration measure, which then applying all the conformal symmetry that we discussed before will be a measure that depends on U and B of this 4-point function, but instead going in this direction, this is then associated to this bunch of derivatives applied to the logarithm of the n equal to star partition function, which is now localized, and it has a very precise matrix model expression. Yes. This is just for normalizing properly this object. I mean, somehow imagine that this is associated to the 2-point function dd. So we are basically normalizing the 4-point function with this 2-point function, which is something that you do usually in field theory in order to somehow get something which does not depend on the normalization of the determinant operator. But in principle, it's a good way also from the sphere point of view to regularize what you are computing. But this is not necessary from the picture that we had in mind. And in the end, we call this object, this function CD of tau bar, and n, because now we have integrated the dependence over U and B. And now this is the integrated correlator that people always refer to. Are there any questions about this review, this picture? We could, in principle, but this becomes still very, very hard. I'm hiding many of the complexity of this process. Somehow this tau D bar are a combination of the original traces, so tau P and tau P bar. So you should somehow rewrite these objects in terms of all the coefficients of this. Somehow what we did in our localization computation is to bypass this process, which also requires the so-called Gram-Schmidt orthogonalization. It's a very complicated structure. And we somehow always, simply insert this kind of determinant operator to then compute the somehow 3-point function that ends up from this numerator. This is something, if you want, I can briefly explain you something more about it, but it's something quite technical. Yeah. Yes. Exactly. It's associated to yeah, this. I agree. I agree. Indeed, we are, as I said, in principle inserting this on the sphere, but we are not inserting exactly this determinant. We are inserting all this combination with respect to these multi-trace operators. So we basically rewrite this in terms of a sum over all the possible multi-trace operators with some coefficients that depend on P somehow. I agree. I agree. I mean, this is the, the form n equal to star partition function, the form with this tau p operator, which are marginal operators. So the good point is that, okay, the mass deformation breaks also conformal symmetry at this level. So here we are breaking conformal symmetry, and we have something which is in principle not even so well defined. But instead, these deformations are associated to this. So it would be written somehow like this, square root of g of trace of phi to the p. And this is a marginal deformation that you are allowed to do even in generic n equal to 2 theories without breaking. Yes, I mean you are not exactly inserting this. I mean you have to exploit the full supersymmetry. These are part of supermultiplets. It's the same story where you somehow do. I mean just for. I mean let's do it for the simplest case, tau on or tau bar. This is actually associated not to trace of phi squared, but to the chiral Lagrangian. And then you use supersymmetry to rewrite this in terms of q to the fourth of trace of phi squared. And so this becomes something which is not integrated, but is basically inserted at the North Pole or South Pole. This is the content of this paper by Gerkovitz, Komargotsky, Pufu, and so on. Yes, basically the same story in higher dimension, but it's again something related to supersymmetry. I mean, it simply requires n equal to 2 supersymmetry. Yes. Yeah. But in any case, you can perform this kind of operation and still get to this class of. Yes, exactly. Okay, let me not mention too much the details about the matrix model that you have seen also in the previous talks. But in general, let's simply mention the fact that this n equal to star localized matrix model is basically it can be seen as a deformation of a Gaussian matrix model up to a one loop determinant, which depends on G on the matrix A, and some instanton deformation, which depend on, and this also depends on the mass, of course, G, A, and M. And we can somehow then apply this kind of derivatives, insert also this determinant operator, write down everything perturbatively in terms of these Gaussian matrix models. This is the most technical point of view, but I will mainly skip this derivation to get to the final result for this CD. We can discuss later if you want some more results about how to compute this kind of object for determinant operators, but let's move to the results. And we start, first of all, by discussing the usual Toft limit, where we consider n to be very large and lambda equal to g squared n fixed, where somehow in this limit, instanton contributions are suppressed. The final result is the following. first of all, the first important point is that we can write this result in the following way. CD equal to an expansion over some coefficient which are CD of G, in this case depending on lambda. And we see, and this is something that we see from this matrix model computation, we have no more this genus expansion in powers of 1 over n squared, but we get something which goes like power of 1 over n, meaning that we are really computing something in presence of a D3 brane. And this is really, at the technical level, something that comes up after the insertion of these determinant operators. So this is somehow the most important point. Of course, these objects are very hard to be computed in the Largent limit, again, due to the fact that these determinant operators have dimension scaling with n. We computed C0 and C1. And now I will give you the results, which are also interesting because they can be written in a way which is kind of familiar. This is an integral of a certain parameter, w, 8w over sinh squared of w, j0 of v minus 1, j1 of v over v. And instead, this C1 is again the same integral, the same kernel, then J1 of V, J1 minus V over 2 minus J0 minus 1 squared over 4, where this V contains the coupling dependence in this way. And we see from these expressions in the 't Hooft limit that we have again this structure that was discussed last week by Grisha also, and also that appeared in many contexts in n equal to 2 theories as well, which is an object, an exact object, which is something like this, an integration over a certain parameter, w, we integrate a certain kernel, depending on w, and then something like j square, where these j are the usual modified Bessel functions. Sorry, j, k are Bessel functions. Yes, I forgot, sorry. So this is, we get a structure something like this, which is very similar to what Grisha was discussing last week. Again, even these correlators enter in this class of objects which are exact in lambda, in the 't Hooft limit, and can be written as an integral over this special kernel. In this case is this sinh square. But in principle, it satisfies this Tracy-Wisdom distribution that he was mentioning last week. And this is also very interesting, but somehow this object is secretly an n equal to 2 object. So this is not so surprising somehow. Yeah, I'm going to exactly discuss that now, yes. Because this is the result in the 't Hooft limit. Sorry? Exactly. We are, just... it was surprising at the end, but the intermediate steps were much more complicated. In principle you can, but there are many technical problems somehow. We basically, our full localization computation relies on the fact that we are able let me just sketch this at this point. Yes. Yes. Yes, but you see, I mean, somehow it's always, I mean, the structure is always of this kind. You have some j squared and some j compared to, for example, the usual structure for these observables, the closed strings observables. In this case, one would have only j squared. And the fact that we have some linear j is really somehow is suggesting that we are doing something different in the dual picture, not just closed strings, but even something more. In principle, I agree with you. It must be something like still combinations of these Bessel functions, I guess, even with the higher degrees somehow, but very random coefficient that we are not able to guess somehow at this point. But yeah, in principle, I agree that, the structure is remarkably simple. And of course, the point of having this exact function in lambda allows to consider the small coupling, lambda going to 0, and this generates the usual expansion in terms of these Riemann zeta values of lambda to the n. The more interesting part is the strong coupling expansion, which is then the one that we can associate to string amplitudes. And the expression here is still quite simple. We have the supergravity result, and then the string corrections somehow. Sum over n, coefficient, again some zetas, lambda to n plus 1/2, and this is for C0, and a similar expansion even for C1. And in principle, just to, since we are in a modularity and resurgence workshop, I just want to mention that in principle, okay, this expansion is convergent, is very well defined, and we can, actually we started from this kind of expansion to then guess this expression, but it's not possible to do exactly the same thing for the strong coupling expansion, because in this case this is not convergent, this is only an asymptotic series, and so it also requires a completion of a resurgence analysis somehow, delta of C0 in terms of this sort of worksheet instantons corrections, which are of this kind, I sum over n e to the minus 2n square root of lambda, and some, again, 1 plus 1 over lambda corrections. The same for the genus 0, the first order in the topological expansion and the second order. But yeah, this is all what I want to say about the resurgence analysis of this expansion. This is nothing too different compared to the previous integrated correlator story. The most important, the most interesting part for the last minutes is now for discussing the actual. Yes, yes. You basically have to use the Mellin-Barst representation of the Bessel functions, and then you close the contour. On the left, you get the perturbative expansion. On the right, the non-perturbative, the strong coupling expansion. And then also from there, you have to add this exponentially suppressed term to actually properly define the strong coupling expansion. But yeah, this is precisely the idea. If we now discuss instead the large n and fixed tau, limit, we can now discuss more properly the modular properties of our result. And what we are going to do is basically a sort of SL2Z completion. And the point that we exploited is that since we know that these determinant operators are associated in the dual picture to a D3 brane, we expect also this limit to somehow preserve SL2Z invariant. So we are still able to, now that we write these objects as a function of tau and tau bar, to realize these expressions in terms of modular functions. And the idea is starting from this result and to promote lambda to 4 pi n over tau 2, being very careful about the two limits that, of course, do not commute. And I mean, the top limit is very different from this. So we have to keep a proper number of terms. But the result that we get is the following: CD of tau, tau bar, and n. It's kind of this approach. Actually, I mean, what we did, honestly, is that we use this result and this SL2Z prediction somehow to compute the one instanton correction. And then we went back to the matrix model. We computed the one instanton corrections numerically, because the instanton corrections for these determinants are very hard to compute. But numerically, we can see that the matrix model perfectly matches the expectations coming from SL2Z invariant. Yeah. We know, we have to return back here, include the instanton now for, fixed tau, right? So we can no more neglect the instanton corrections. We compute the instantons, and we, at this point, perform this matrix integral numerically. So we do it for large values of n, and we extrapolate the large n expression of this full expansion to match the SL2Z prediction. And this is how we actually realize that, the final answer is still SL2Z invariance. In principle, even without computing explicitly the instanton corrections from the matrix model, SL2Z and the expansion in terms of non-holomorphic Eisenstein series allows to. Yes. Yes, exactly. Yeah. We really compute, we input the Nekrasov instanton partition function, the one instanton contribution, which is there when we consider this limit, and we compute the one instanton correction from the matrix model. We have a certain result, and we compare this result with the prediction. Yes, exactly that, yes. Okay, so let me write the result and to then give an interpretation. This is the supergravity result, and this is the first string correction. So supergravity first string correction. We have a log n term, which is expected also from the brane scattering perspective. And then we have the additional stringy corrections, which are pi tau 2 over 3 minus log tau 2 minus 1 over n 3 over 2 zeta 3 tau 2 to the 3 half over pi to the 3 half plus order of n minus 3 over 2 minus 2 in principle. And so here, exactly, we recognize the supergravity and the first string correction. And then we have these two objects that we can recognize to be the zero mode of the E1 non-holomorphic Eisenstein series. And this is the zero mode of the E3 half. So somehow this explicit result suggests which are the modular functions appearing in this expansion. And the interesting fact is that compared to the closed string case, in this case, this object was given purely in terms of E of n plus 1/2, only half integers Eisenstein series. Here we also have this regularized first Eisenstein series. And we actually, at this point, compare our result and this interpretation in terms of brane string amplitudes with the literature. And we have seen that actually this matches the expectations coming from brane string amplitude. These are results by many people. I will for sure forget someone. Bacchus, Bain, Michael Green, Gatperl, and also more recently, Lin, Shao, Wang, and Jin, where they basically realized that for these brane string amplitudes, the first string corrections are exactly E1 and E3/2, where in particular, this is associated to the alpha prime squared R squared correction to the effective action, and this is associated to alpha prime cube D squared R squared from, the brane string scattering amplitudes perspective. And so somehow this computation, which, as I said, comes purely from a field theory perspective, matches the expectation coming from brane string scattering amplitudes. Would you? Yes. Yes, I mean, in principle, they should be combined by Nekrasov partition function in a, I would say, very non-trivial way. In principle, yes. At the moment, I don't have this clear picture of how these two things can be discussed separately, I would say. But I mean, that's an interesting question. I honestly don't know. But in principle, yeah. Go, sorry. Yeah, somehow the picture, yeah, I forgot to to draw it properly. But the picture is that, as I said at the beginning, this is really, I mean, the D-brane setup is not fully clear from these determinant perspectives. But once that you insert these two determinants and 2O2, this somehow, in the larger limit, generate this extended object, which goes into the heart of ADS. I hope this is clear. And what we are computing is basically this scattering amplitude. So it's 1 D3 brane, yes. So we are really computing something like D3 and then O2, O2. I mean, the corresponding operator to this O2, O2. Absolutely, yes, absolutely. Indeed, they are actually computing these corrections, exactly, without having the somehow I mean, the curvature corrections. I mean, they are not seeing that. These people actually, they guessed from supersymmetry. This is a more recent paper in 2015. They guessed from supersymmetry that these are the correct coefficients for this term and this term, but in flat space. Something like this, yes, yes. Yes, something like this. I don't know the full details about these papers, but yes, I guess this is more or less the picture. The first term, this is the supergravity. And if you want, this is really, I mean, something very sketchy, but I mean, depending on normalization and so on, usually what people get from other integrated correlators of closed strings is something which is 4. So somehow this is half of that. I don't know if this is something actually relevant because as I said, this is subject to possible different normalization, but it looks consistent. And these are constants. This is the Euler-Mascheroni constant somehow, which are somehow reasonable from the string correction of the supergravity limit. And but yeah, I don't have anything more profound about this from the dual picture. So yeah, I think I can stop here for the moment, and thank you for the attention. Yes, yes. Because yeah, no, we are keeping lambda fixed. So somehow they are weighted like yes, the exponential. I mean, it becomes something like n minus n over lambda, something like this. And so they are exponentially suppressed. But if you now use the other limit, this becomes something which is fixed, and so you're not allowed anymore to suppress them. Yes. Yes. Yes, okay. Let me very briefly sketch at least the way we computed this. Because yeah, I agree that if not, it looks something coming out of the blue. But somehow, the idea is that once that you perform any kind of insertion, any kind of trace insertion, you have to pay attention to many things. But the most important one is that the theory that you have on the flat space is different from the theory that you have on this for sphere. And so you have to perform this Gram-Schmidt orthogonalization procedure that somehow requires to disentangle any operator with dimension p. This is not associated exactly to trace of phi to the p, but it's associated to this. I mean, somehow this is associated to this plus coefficients and then correction with all the lower dimensional operator. So if you now think about this process to be done for objects which have dimension n, this becomes extremely hard and honestly kind of impossible to do in this way. So what we did is to formally insert the operator simply in this object. So we simply compute this somehow. And this object, starting from this partition function, can be written in this way. A, G is this kind of operator. Then we plug the mass to 0. This operator is an infinite sum over all the loop orders, can be written perturbatively, some coefficient CL. Of course, we have lambda at this level, only G and Mills to the L, and then all the possible operators appearing OL of A. And we have to compute this object in the Gaussian matrix model. And we have dropped the instanton correction. Yes. Somehow, this is due to the structure of this one loop determinant, which is, I don't fully remember the expression, but it's a combination of these Barnes G functions that can be rephrased in that way. So, yes, I mean, very, very briefly, I mean, it's a combination of these Barnes G function depending on the eigenvalues of the matrix, plus M, A minus M, something like this. You can perform this derivative with respect to, I mean, to this mass, and you rephrase the final result in terms of these traces, A to the L. But the technical point then, I mean, you have, I mean, this is already quite complicated. Actually, this includes not only the single trace, but all the multi-trace operator that, of course, this is an infinite sum. And we now simply insert these determinant operators formally here. And we compute then this object in the Gaussian matrix model. This object now can be somehow computed by performing this Gram-Schmidt orthogonalization procedure on these operators instead of these operators. So you perform this Gram-Schmidt here and not here. You have different coefficients, but the final formula that you have to compute is a 3-point function in a Gaussian matrix model, so in a free theory. And this object can be computed using weak contractions. Okay? And so for each order in perturbation theory, you have to compute these 3-point functions, which are fixed by supersymmetry. And at this point, these are really flat space 3-point function that can be computed using the old school techniques coming from Rangulan and other people that computed actually these objects using, I mean, symmetric group techniques and so on and so forth. But there are results for this 3-point function, which is fixed in the flat space. So this is how, I mean, somehow the quantum corrections are then contained here, and this is computed in this free theory. We do this for many loops order, we have many results, and we can then guess the exact result for C in terms of this convolution of Bessel function. This is more or less the idea. I can give you more details if you want then, but it's a very special trick. Instead of considering this, this Gram-Schmidt here, you perform it there, and you trade the integrated 4-point function with an infinite sum of 3-point functions. This is briefly the technical point. Yes, not so much more. The point is that compared to the previous case that Grisha was discussing last week, here we have this additional J contribution, some parameter and a certain. Somehow, this is the only novelty compared to the previous results for the integrated correlator, the fact that we have also this linear term, which is not a technical problem somehow. It's interesting because it somehow realizes this expansion not in terms of 1 over n squared, but in 1 over n. The good point is that still we are in the same realm of observables, which are there in n equal to 2, n equal to 4, which have this kind of expansion. In principle, what one could use his techniques, their techniques, to refine somehow all the resurgence analysis and go much beyond what we did in our paper, for example, for this exponentially suppressed correction. This is, I think, the most technical achievement that, yes, one could do also at this level. Thank you.